Okay, so welcome to lecture 13 of our video lecture series for Physics 2. So today's video lecture series would be on magnetic force and magnetic field. Okay, so for today's discussion, we will be presenting the following ideas and the following topics. So we have magnetic force, finding the direction of the magnetic force, magnetic field, magnetic field lines, magnetic flux, motion of charged particles in a magnetic field, magnetic force in a current carrying conductor. Okay, so let's start with the first topic, the magnetic force. A magnetic force, of course, acts only on moving charges with velocity or moving charges and is perpendicular to both velocity and magnetic field. Uh, there are four key characteristics of the magnetic force. Number one, the magnetic force is proportional to the magnitude of the moving charge. So this means the greater charge is being carried by the particle, the greater the magnetic force that it will experience. Number two, the magnetic force is proportional to the magnitude or strength of the field. So this means that the greater the strength of an established magnetic field within a given region, the greater the magnetic force that any charge that will enter this region of the magnetic field. Okay, so number three, the magnetic force also depends on the particle's velocity. So this means the greater the velocity of the moving particle that enters the magnetic field, this means that that particle will experience a greater amount of magnetic force. Now, number four, the magnetic force is proportional to the component of the velocity perpendicular to the field. What is said in the first part of this slide is that the basic requirement for the moving charges that would enter the magnetic field is that the velocity is always perpendicular to both the magnetic force is perpendicular to both velocity and magnetic field. If it happens that the velocity is not directly perpendicular to the magnetic force, only the component of the velocity perpendicular to the field will influence the magnetic force. Okay, so combining all these four key characteristics into a working equation, we will have the computation or the quantification of the magnetic force as F equal to Q V perpendicular times B. Now, so from here, F represents the magnetic force, Q represents the amount of charge of the charge that enters the region where there is an established magnetic field. V is the velocity of that charge, and B is the magnetic strength of the magnetic field of the region where Q enters. Now, of course, V perpendicular, just like what is said in the first statement of this slide, that the magnetic force is perpendicular to both velocity and magnetic field. So this means F is perpendicular to both velocity and B. B here represents the magnetic field. Okay, so but if it happens that the magnetic field and the velocity are not directly perpendicular to each other, then we simply compute for the component of the velocity that is perpendicular to B. Now, this component would be the component of the velocity that will only influence the amount of force that will be experienced by the charge. Okay, so this formula enables us to compute for the amount of force that will be experienced by a single moving charge. Okay, so these are the corresponding symbols. So we have F as the magnetic force that is expressed in the unit Newton. Q is the charge. This should be in coulombs. V is the velocity, which is in meters per second. Of course, the angle phi is the angle in between V and B. B is the magnetic field. The magnetic field, by the way, is expressed in the units Tesla or Gauss in honor of the Serbian-American scientist Nikolai Tesla. Okay, so in terms of the relationship between Tesla and Gauss, Tesla is the higher unit, where Gauss is the lower unit. Just like Newton is the higher unit for force, while dynes is the lower unit. Just much like meters and centimeters, meters is the higher unit, centimeters is the lower unit. So between Tesla and Gauss, Tesla is the higher unit and Gauss is the lower unit. Okay, so of course, 1 Tesla. From our formula of the magnetic force, we can solve for B. B could be B is if we're going to solve for B, B is equal to F over Q over V. So therefore, the unit Tesla would be expressed in terms of the combination of units of force, charge, and velocity. Okay, so 1 Tesla is defined as 1 Newton over ampere meter. Okay, so let's focus more on different scenarios of how will a charged particle would enter an established magnetic field, and how would this charge entering the established magnetic field experiences the force by virtue of the magnetic field. Okay, so let's take the first scenario. We have a positive charge that enters an established magnetic field. When the charge enters the magnetic field, it enters parallel to the magnetic field. So from here, if we're going to apply the formula for the force, the force would result into a zero value. So since if we're going to consider the angle in between the velocity and the magnetic field, for this scenario, the angle in between, if the positive charge enters the region parallel to the field, therefore the angle in between the velocity and the magnetic field is zero. So if we plug in that value in sine phi, that would be sine zero. Sine zero is of course is equal to zero. So this means this whole quantity is equal to zero. So the force is equal to zero. This means that the charge, once it enters the region of the magnetic field in such a way that it enters with a given velocity parallel to the magnetic field, the force would be equal to zero. This charge would not experience any magnetic deflection. So this means that the charge would simply go straight through the magnetic field without any deflection from the field. Okay, so for the second scenario, we have the same charge, same positive charge, but this time it enters the region of the magnetic field at a given angle, at a certain angle. So for example, here, as illustrated here, the charge enters the region this way, as indicated by the green arrow. Okay, so since there is an angle in between the magnetic field B and the velocity V, therefore our formula for the magnetic force F will no longer be equal to zero, since sine phi is not equal to zero, since there is a value for the given angle. Now, of course, this means that if you have a maximum value for phi, which is 90 degrees, your sine phi would be a maximum value, sine 90. Sine 90 is equal to 1. This means that the product Q times B would have its maximum value, and therefore F would have its maximum value. Okay, a charge moving at an angle phi to a magnetic field experience a magnetic force with the magnitude F is equal to Q times B times B. Okay, so let's consider the third scenario. The third scenario is when the angle in between V and B is directly perpendicular to each other. So that means that the angle is 90 degrees. So sine 90 degrees gives you 1. So 1 times Q times V times B gives you the maximum value of the product QVB, and therefore this becomes the maximum value of the magnetic force and the magnetic deflection. Okay, so let's take this sample problem. A beam of protons moves at 3 times 10 to the 5 meter per second through a uniform field with a magnitude of 2 Tesla. that is directed along the z-axis. The velocity of each proton lies at an angle 30 degrees to the z-axis. Find the force on the proton. Okay, so this problem involves simply direct substitution of the values in our equation. So simply what you just need to do is to plug in the values in the formula. So in our formula, QF is equal to QVB sine P. Q is presented as the proton in the given problem. So our charge is proton. Of course, the charge of the proton is 1.6 to the negative 19 coulombs. Multiply that with the given velocity. The velocity is 3 times 10 to the 5 meter per second, and times b. B is given as 2 Tesla, and there is an angle between V and B. The angle is 30 degrees. So therefore, you make use of this form of the formula, Q times V times B sine phi, that is sine 30 degrees. So therefore, multiplying them together provides you the value for F. Okay, so I'll just leave you the hand for the computation. So although I have described it to you here, I'll be leaving this to you for your own exploration of the answer. Okay, so next thing to be concerned about is how do we determine the resulting direction of the deflection of the charged particle when it enters the region with experiencing a magnetic force due to the presence of the magnetic field. So how do we find the direction of the magnetic force? Okay, so at this point, let me introduce to you what we call the right-hand rule. So the right-hand rule is our convention for determining the direction of the magnetic force on a positive charge moving within a given region of an established magnetic field. Okay, so the right-hand rule is used whenever the charge that is entering the field is positively charged. Now, if the charge happens to be negative, of course, we will be using the left-hand rule instead. Okay, so at this point, we'll just be focusing first on the right-hand rule. Okay, so our right-hand rule is initially your our forefingers, just like what is illustrated here, our forefingers, you set your forefingers towards the original direction of your velocity. So for example, if this is the direction of the velocity, the forefingers should be pointing towards this direction. Okay? Okay, so the next step in determining, doing the right-hand rule is that you will be curling your forefingers towards the direction of the magnetic field. So if your forefingers points towards this direction, you will be curling your fingers towards the direction of the magnetic field in a sort of grabbing motion. So you will be curling your fingers in a grabbing motion, just like when you grab something. Now the direction of the grabbing motion would be towards the direction of the magnetic field, and of course, your thumb would be sticking outwards, and the thumb would point towards the direction of the magnetic force. Now, doing this curling action virtually points towards the direction of the magnetic force and towards the direction of the deflection of the charge due to the presence of the magnetic field. So, which means if you're going to apply the right-hand rule for this setup, the forefingers would be pointing towards here, curling towards the direction of the magnetic field, and your thumb should point towards the upward direction. So therefore, this would be the direction of the magnetic force. Try to notice that the direction of the magnetic force is always perpendicular to the plane containing both velocity and magnetic field. Okay, so let's try that again using the second scenario. So we have the same positive charge, but this is moving towards this direction as indicated by the green arrow. Now, the velocity is still pointing towards this direction. Now, making use of the right hand rule, again, the right hand rule is that you need to point your four fingers towards the direction of the magnetic the velocity. Now, what you do is to curl your four fingers towards the direction of the magnetic field, and your thumb should be pointing outwards, pointing towards the direction of the magnetic force. Now, what is illustrated here in this second diagram is that you will be actually choosing between two angles. There is an angle here, and there is an angle which is outside this circle. Okay, so choosing between these two angles, you are actually the right hand rule actually works by in application that you will be using it with the smaller angle between the two. So between this angle and this angle, this angle here is actually the smaller angle among the two. So for example, between the using the first diagram, this angle here and the outside angle, this angle is actually the smaller of the two angles. So you apply the right hand rule. Uh, the curl of the fingers should be towards the curl in the direction of the smaller of the two angles. So this means if you apply the right hand rule for the second diagram, the curl of the four fingers would be pointing towards this direction, curling your fingers in a grabbing motion in the direction towards the direction of the magnetic field. Your thumb should point towards the downward direction, pointing to the direction of the magnetic force or the magnetic deflection. Okay, so for the left hand rule. Okay, so as mentioned earlier, the left hand rule would be um, the application of the right hand rule, but this time the left hand rule for negative charges. So the same rule applies. The direction of the four fingers would be pointing towards the direction of the velocity. You will be doing the grabbing motion of the curl of the fingers directed towards the smaller angle between the velocity and the magnetic field, and your thumb should be sticking out, and the thumb would point towards the direction of the magnetic force. So for this diagram, doing that, your thumb should point towards the downward direction, while for this second diagram, your thumb should be pointing towards the upward direction. Okay, so I suggest that you do the left hand rule for the diagram and the right hand rule for the previous diagrams, so that you could somehow grasp the idea of performing the left hand rule and the right hand rule. Okay, so the magnetic field, like the electric field, the magnetic field is a vector field. So therefore, there is an associated direction for every point within the vector field. The magnetic field is denoted by B and has the unit Tesla or Gauss. The magnetic field can be represented by what we call a magnetic field line or magnetic field lines. Of course, just like what was presented earlier, the magnetic field can be computed from the computation of the force by dividing force by Q over V, or Q over V sine phi. Now, the magnetic field lines, just like the electric field lines, are representative lines that represents the strength of the magnetic field at a given region. Of course, the idea is that if you draw the magnetic field lines closer to each other, that means that the strength of the magnetic field within that region is actually stronger as compared to the other regions where the magnetic field lines are drawn far apart. Now, in terms of the direction of the magnetic field lines are conventionally drawn pointing outwards from the North Pole and pointing inwards to the South Pole. Now, unlike the electric field lines, remember the electric field lines when we have presented it during the discussion on electric fields. For positive charge, the electric field is actually pointing radially outwards in all direction, while for negatively charged, the direction of the electric field lines are pointing towards the direction of the negative electric charge, pointing inwards in all direction. Now, the electric field lines virtually extends indefinitely in all directions, coming out of the positive charge and coming inwards into a negative charge, extending to infinity. Now, comparing that with the magnetic field lines, the magnetic field lines actually does not extend to infinity but forms loops around the magnet. Okay, so just like what we see here, that this line here actually forms a loop within the magnet. So the same goes with the other lines that are represented here. Although, of course, what we see here is simply the region that is represented here, but these field lines would actually extend so that it would eventually form a loop around the magnet. Now, as for magnetic field lines that is produced by current carrying conductors, what we see here is that if you're going to apply the right-hand rule, the right-hand rule would actually point to the direction of the magnetic field. So if you're going to apply the right-hand rule, the grabbing motion of the right-hand rule, you will be grabbing the portion of the current carrying conductor, pointing your thumb towards the direction of the current. So for example, if this is the direction of the current and you apply the right hand rule here, you will be doing the grabbing motion towards this direction, pointing your thumb towards the direction of the current. Now the direction of the curl of the fingers would actually point towards the direction of the magnetic field around the current carrying conductor. Okay, so notice that the field of the loop, if you do many loops, that would actually reinforce the strength of the magnetic field, so that you will end up with a stronger magnetic field. And try to notice the reinforced magnetic field and compare that with the magnetic field of the magnet. Virtually the form of the magnetic field of a bar magnet, compare that with the magnetic field formed by the corresponding loops of wires. They are virtually similar.